So this is me, I'm principal consultant at Red Siege. I've been in IT a really long time now. And as a gentleman said yesterday, he likes to spend as much time as possible away from a computer. That's me. I hack so that I can go out in nature, and I'm a photographer, so I like to do those things. This is a slide that should have been taken out, but if you like Red Siege swag, if you've ever got one of our stickers or one of our t-shirts, give Jaycon a shout, because he makes it all possible. If you want to copy the slides, you can get them at redsiege.com/hiding. And what we're going to talk about today, what is shellcode? Why do we have to hide it? How can we go about doing that? And then some other ideas at the end. But redsiege.com/hiding, and I will show you that link again at the end. So, shellcode, vastly oversimplifying here, but it is a small piece of code that we use as the payload. Historically, when you think about like buffer overflow exploits and things like that, shellcode was a little bit of code that actually gave you a command shell that would allow you remote control a system. The way I'm talking about shellcode here is it's the code that loads our C2s, whether it's Cobalt Strike or living off the web C2 or whatever it is. It's the code that loads, it is our payload. And we typically store that as hex in a program, but we also see it stored, you can store it as ints. You could even store it as raw bytes. If you want more information, Wikipedia's got an article on it. So, before we get started, I'm going to be talking about example programs that I wrote that contain obfuscated shellcode. And that program, all it does is contains the obfuscated shellcode and then deobfuscates the shellcode and prints it out to the screen to verify that it did it correctly. I didn't actually try to execute any of the shellcode because I uploaded all these samples to VirusTotal to see how they performed. And I didn't want the VirusTotal engines signaturing on the code execution part. So all I want to do is know, can they identify my obfuscated shellcode, and importantly, the routine that's used to deobfuscate the shellcode. So why do we need to hide? So if you're using any kind of well-known framework like Metasploit or Cobalt Strike or BruteRetel, that's the name of it, couldn't remember. BruteRetel, any of those kinds of things, those are going to have byte sequences that are signatured. Even if you're generating a new payload every time, there's parts of the shellcode loader, because the shellcode contains a bootstrap that helps it load itself and run, and those bootstraps are going to be signatured. And if you just stick unprotected shellcode in your loader, you're probably going to get busted. So we need to obfuscate our shellcode so that we can get code execution. So this is an example from a program called ThreatCheck. What it does is it does this binary search method to identify the exact bad bytes in a file. It submits them to Defender looking for a signature. So this is an unobfuscated example program that contains unobfuscated Metasploit interpreter reverse HTTP payload. And you can see right here it says like these are the bad bytes, ends in A256FFD5. And sadly, it was like, this is good or bad depending on how you look at it. It was detected by 27 engines, but it was only detected by 27 out of 72 engines on VirusTotal. And this is unobfuscated interpreter. Like, everything in the world should detect this. And what's really sad about this is that 27, it was actually 23, and then I modified the program to do the most basic code execution, where you allocate memory, copy shellcode in, and run create thread to actually execute your shellcode. And it was only 23, and then I added that bit to it, and only 27 detected it. So like, this is both like good and extremely sad that only 27 detected that. So if we want to hide, if we want our shellcode to not get detected, and let me be clear, I'm only talking about ways to protect the shellcode. Everything else about your shellcode loader still has to be OPSEC safe. It has to be undetected. This is just protecting the payload portion of it. We can encode. We can encrypt or we can do some other kind of obfuscation. We can also separate our shellcode from our loader to make that maybe a little bit more safe, have them in 2 different locations, but even then, you probably still have to protect that shellcode that is separate. So the first example is base64 encoding. Someone asked me about that the other night, and yeah, I did try base64, and it's not great. Pretty much 18 of 72 engines detected that, so base64 is an encoding mechanism that you could use, and it would work, but it's not a really good option. So let's go old school encryption. So we have something called a ROT cipher, like ROT13, also known as a Caesar cipher. So this goes back like 2,000 years. This encryption routine's been around. And the way it works is, if we're talking with the alphabet, let's say you have an A. If you're doing ROT13, you shift 13 characters over. So that becomes, what, an M or an N, I think? One of those two. So N. And if it was ROT1, it would become a B. ROT2, it would become a C. So all you're doing is shifting the alphabet over. If you hit the end of the alphabet, you rotate back around. And you can do the same thing with your shellcode. And you do that to encode it, and at runtime, you just subtract whatever offset you were using, and away you go. And surprisingly, only 7 engines detected an interpreter payload that used ROT13. Like, come on, man. Like, this is really sad. So we can go a little more modern encryption. So XOR or XOR, the way it works is you have a byte and you XOR it with a key, and then you have your value. And you can do the XOR again, and you get the original value. So you can it's reversible encryption. And it's really simple. This is just the code that we would use to decode our shellcode and get it back to our normal form. And actually, it's the same code that you would use to encode your shellcode. And being that it is incredibly simple, it should be very easily detectable. And surprisingly, only 8 detected that. So it's not great, it's not your best choice to use, but depending on what your target's using, it may be okay. But let's be a little more advanced. Let's do a XOR, but let's use a multi-byte key. So the way that works is you have a value and you have a key. So let's say the key is ABCD. You encode or XOR the first byte of your shellcode with A, and the second byte of your shellcode with B, third with C, fourth with D. The fifth will be A again. So this running key cipher, like the key just keeps repeating the same length as your payload. So how does that work? Incredibly well, with the gotcha that this routine here is signatured, and I actually had to throw in some junk code to throw off the signature, and I'll talk more about that later in the talk. But it is signatured, but it worked incredibly well for a very rudimentary way of obfuscating your shellcode. So 2 out of 72, that's good. What about AES? AES encryption is way more secure, so it must be better. In fact, not so much. Scooby was talking about Rust. If you're writing payload loaders in Rust, and I haven't tested this in a while, but when I first started doing it, if you wrote Rust code and you imported the AES or ARC4 crate, you didn't even have to use it. Just by importing it, it resulted in a detection, which was kind of wild. This detection is probably not because of that. It's something called entropy, which we will talk more about later in this talk. So one benefit of using AES is that sometimes when you're writing a shellcode loader, vendors like EDR vendors are looking for things to happen in a very specific order and in a short time period. So if your loader allocates memory, copies shellcode, and it executes it just like bang, 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 that is a very commonly detected signature. So what some vendors do is they look for it to happen in a certain time period. But they have to make these trade-offs. Watching a process for an extremely long period of time can be a performance impact. So if you make things take a long time, they may know about, and they may not follow you anymore. So if you put your AES key in, but you leave off the last 2 bytes of the AES key and you brute force those, takes anywhere between like 5 and 10 minutes. It takes about 5 minutes on my laptop to brute force a Cobalt Strike beacon to come up with that key. So now you have a built-in delay that you can use. So you have the entropy problem, which I just mentioned, but we'll talk about ways to get around that. But actually, we don't in this talk. That was a talk I gave last year, I think, actually. So, but it's a way that you can build in that delay. So that might be a reason that you choose AES over something else. Pro tip, always use the smallmouth bottle when you're presenting. It's always fun presenting with just a chest full of water. So I mentioned RC4, or ARC4. This has some benefits that you might want to take advantage of if you're writing Windows shellcode loaders. There is a DLL called ADV API 32, and it has two functions, system function 32 and system function 33. And what these functions do is they encrypt something using ARC4 and decrypt using something, or decrypt something that's ARC4 encrypted. Now, I am not an encryption expert, but it seems to be that ARC4 functions like XOR because you can use either one of these interchangeably and they work. So you can ARC4 encode your payload and then call one of these functions to decode your payload. So maybe you want to use ARC4. It's really simple to use and it's not terrible. It's not the best, but it's not terrible. 7 out of 72, so less than 10%. So what about two arrays? Let's take our shellcode and split it into two arrays. And we're going to split our shellcode into two arrays based on the shellcode's position in the array. Because typically our shellcode is represented as like an array of hex characters. So we're going to create two arrays, an even array and an odd array. But I'm not talking about the value of the shellcode. I'm talking about its position in the array. So your first byte of shellcode is at position 0, so that's going to be an even. So you put that in the even array. The second byte of shellcode goes into the odd array, and then the third byte goes into the even array, fourth byte into the odd array, so on and so forth until you've broken up all your shellcode. And it looks something like this. So typically, like a Metasploit shellcode loader, the preamble is going to be FC 48, 83, E4, F0. It's going to look like that pretty much every time. That's what I'm talking about, like signatured bytes. That's what we're talking about here. So this is what it would look like when it's done. And unfortunately, it's not real great. It's not terrible again, but it's not real great. But it's an option for you that you could use. So what about flipping it? So I just said that shellcode starts out with FC, 83, E4, whatever it is. Let's reverse our array. So now we're going to end with D5, FF, so on and so forth until we get to E4, 83, 48, FC. So all of the bytes have just been put in reverse order. And to use that, we're just going to read that array from the end and copy it into our new shellcode variable and execute it. And that works surprisingly well, like really surprisingly well. So then I thought, what about taking the shellcode and instead of it being an array, actually being a string? So it's going to be like 0xfc, comma, space, 0x48, comma, whatever it is, right? So it's a string. And then let's reverse that string. And you have to do some gymnastics to like read that and split it. And I've got a whole blog on it that I'll post the links to later. But you could do that and store that. And surprisingly, that did not do well at all. So apparently people have tried this and it's been signatured. So, excuse me, I really did not expect that. It was not very effective. So what about camouflaging it? Let's make our shellcode look like something else. How do we do that? Well, we'll talk about a few ways to do that. So a UUID, a universally unique identifier, you may have heard the term GUID as well, globally unique identifier. UUID is the new way of calling it. It's a 128-bit label for information that theoretically, if you use a UUID to identify your things, you'll never have a collision, right? Like the key space is so large, you'll never have a collision. So this was actually used in the wild. 2021, January, the Lazarus group was using a novel shellcode encoding technique, and then an execution piece as well. But we're going to talk about the encoding technique here. So this screenshot is taken from Bobby Cook's GitHub repository, and you'll see here our shellcode is FC4883E4, so on and so forth. So to be a UUID, it needs to be structured in a certain way. So we've got 4 bytes, 2 bytes, 2 bytes, 4 bytes, and then whatever the remainder is there. But it's not just structuring them in those byte groupings. We actually have to do a little bit of gymnastics. So you'll see FC is at the end, 48. So these first several sections of the UUID are actually backwards. But the reason that Lazarus used this, I talked earlier about how a shellcode loader works, right? You need to allocate memory, you need to copy memory into that buffer, and you need to execute it. So the ways you copy it are usually marshal.copy, RTL move memory, or RTL copy memory. You don't have a huge number of options available to you. And that pattern is very well recognized. Even if they don't recognize your shellcode, they see that pattern, they being the enemy, the EDR vendors and the AV vendors of the world, they see that pattern, they know that something bad is going to happen because this doesn't happen with normal programs. And the reason that they used a UUID is because this function UUID from string A. So what UUID from string A does is it takes a string representation of a UUID, converts it into binary, and copies it into a memory location. And that memory location is going to be the buffer that you allocated earlier in the process. So now you're copying your shellcode into memory without using one of the signatured sequences, right? Like we don't have to call marshal.copy or RTL move memory. We're now using this routine to copy our shellcode into memory. Breaks that signature. How well does it work? Unfortunately, this one got a lot of attention. So it doesn't get by really any of the major EDR vendors out there. But what if there were other data types that we could mimic and that had a same pattern? And in fact, there are several other API calls. I started searching for this, and I found old GitHub repository from Orca 666 called Hellshell. It's the first place that I saw this implemented. And there are 3 things we can do. I said we could store our shellcode as integers, so we could store our shellcode as an IPv4 address. We could store it as an IPv6 address, or we could store it as a MAC address. And there are 3 convenient functions: RTL IPv4 string to address A, IPv6 string to address A, and RTL Ethernet string to address A. And all of them only had 6 detections. And the only difference is that API call. Instead of using UUID from string A, we're using one of these. So this might be an option for you if you need to if you need to hide your shellcode and copy it into memory. And if you're a defender and you see an unknown binary that's full of MAC addresses or thousands and thousands of IP addresses, that might be suspicious. You might not know what else is going on, but something's not right. That's really weird. So I mentioned earlier about entropy. So when I need to hide my shellcode, and if I choose to use encryption, I increase entropy. Entropy is a measure of the amount of randomness that's in something. So if something is very random, it's said to be high in entropy, and if something is low in entropy, it's said to be non-random or not very random. So if I use encryption, I increase entropy. But there are EDR vendors out there that look at unknown binaries and look at their entropy. And if the entropy is really high, you can make an educated guess that there is encrypted data in this thing that you're analyzing. And why is it encrypted? That might be unusual, especially when you look at a shellcode loader that doesn't do much. It allocates memory, copies it into memory, copies your shellcode in memory, and executes it. That's really all your shellcode loader does. So you have a very high amount of encrypted data, and a very low amount of code. So really high entropy, and EDR vendors will say that's suspicious. If you were here last year, I think I gave a talk on a tool I wrote called Jargon, and that, in fact, I found out about all this because CrowdStrike was measuring entropy and wouldn't allow my payload to run because I was using AES encryption, so I had very high entropy, low amount of code, and it said, I don't know what you are, but I'm not gonna let you run. So we encrypt to hide, but when we encrypt, we increase our entropy, so we get caught. So like, how do we break this cycle? How do we get out of there? So I wrote a tool called Jargon, and Jargon defeats entropy checks by using English words. Words in languages, doesn't matter what the language is, languages are not random. We can actually measure this and test this, but languages are not random. So if you take a bunch of random data and add a bunch of non-random data to it, mathematically, entropy goes down. So the way that Jargon works is it creates, first I need to create a translation table. I'm going to need 256 unique words. Why do I need 256 unique words? What's that? For the bytes, because there's only 256 possible byte values, right? 00 through FF. There's the only possible values for my shellcode. So I need 256 unique words. And if I have 256 unique words and I put them in an array, each word's position in that array represents a byte of shellcode. So whatever word is the first byte of the array represents 0x00. Whatever word is in the second position represents 0x01. And the word that's in the last position in the array is 0xFF. So I wrote a blog about Jargon. You can read more about that there. But that actually works really well. Oh, this is an example, that's why. Forgot what's happening here. So this is just some example shellcode. Imagine I have 5 bytes of shellcode. My translation table only has 5 words in it because I only need 5 words for this example. So my words are day, dog, cat, fish, and horse. So these words represent 0x01, or 0x00, 01, 02, 03, 04. Those are all the bytes of my shellcode. So if I ran through a hypothetical example, we see cat in the first position. If cat's in the first position of my translated shellcode, my obfuscated shellcode, then I know that that byte value is 012, 0x02. I know that it has to be that because of this translation table. And that's how Jargon works. It runs a loop, it generates 256 random words, and then it just iterates over your shellcode, looking up the word that corresponds with that position. And so your payload doesn't have any shellcode in it. It has a translation table full of English words and translated shellcode full of English words. And because those words are not random, languages are not random, your entropy is very low. And then you just reverse the process and you execute your shellcode, and you don't have the entropy problem. And in fact, it works quite well. Only 3 engines, and this tool's been out. I wrote, the blog series that this talk is based on, I wrote earlier this year, probably around April maybe, something like that. And as of April, only 3 engines had detected that, and the technique's been out about 2 years. So not a lot of people are looking for it. The signature was, the decoding routine was signatured, and I had to change it a little bit. And again, we'll talk about ways to break that pattern. But Jargon is not widely detected yet. And again, if you're analyzing this binary, you're looking at it, there's just a huge amount of words in it. That seems a little weird. If you really want to screw with an analyst's head, extract 256 unique words from kernel32.dll, and you have a payload full of function calls. Like, what is happening here? This is really weird. So after I wrote Jargon, I wanted more options. I wanted more options in my toolkit. So I was thinking about, how does that work? What can I do that's not traditional encryption and obfuscates my shellcode and isn't well detected? My wife likes to do jigsaw puzzles, And so if you think about a jigsaw puzzle, you've got a bunch of pieces, right? And they come in a box with a picture on the front. The pieces are all scrambled, but using that picture on the front, you can start to put it together. If someone hands you a bag of jigsaw puzzle pieces and you don't have the box, you don't know what the picture looks like, you can still get it back together eventually through brute force, but it's going to be much harder. But if you have that picture, a map of how to put the puzzle back together, it's a lot easier. So I started thinking about, like, how could I make that work with shellcode? So what I do, most of my loaders, my programs for doing encryption or obfuscation are written in Python. So I'm using a list, which is kind of like an array in other languages. So what I'm going to do is I'm going to create this list called positions, and I'm going to populate it with 10 values starting at 0. So I'm going to have 0 through 9 in this example. I need it to be the same length of my shellcode. So however many shellcode bytes I have, that's what that's going to be at the end. In this example, it's 10, but you know, if it's 200,000, it's going to be 200,000 at the end. Now I call random.shuffle on positions. So that's going to shuffle that positions list into some random order. So now, instead of being 0 through 9, I've got 1, 6, 8, 2, 5, 9, 7, 0, 4, 3. So now I can begin constructing my payload. My obfuscated payload is going to go in this variable called jigsaw, and I'm going to iterate over positions. So 4 positions, so for each unique value in the positions list, append onto jigsaw the byte that is at shellcode position. So the first byte of my jigsaw is going to be shellcode index 1. And the second one is going to be shellcode index 6, shellcode index 8, so on and so forth. So when this is done, I have all the bytes of my shellcode, but they're stored in a random order. So now it's just scrambled bytes. I haven't tested this to see if it actually increases entropy versus the unencrypted or unobfuscated version. That would be a good test. I should have done that. I didn't. I apologize. But I've now have this randomized list of shellcode. So when I want to use it, my payload is going to have a variable called jigsaw that stores all of the obfuscated shellcode, and then my map, positions. So this is that picture on the front of the box. This is the key to putting it back together. It's just like the translation table with jargon. So I'm going to iterate over the positions array. I'm going to look up the value that's there, and then I'm going to have this new value, this new array called shellcode. That's where I'm going to store my reconstructed shellcode. So in shellcode position, insert to jigsaw IDX. So we're going to start at 0. So IDX is going to be 0. So I'm going to read from jigsaw index 0, and I see my position is 1. So I'm going to grab that value and store it, whatever value is in jigsaw index 0, I'm going to store it in shellcode index 1. And then whatever value is at jigsaw index 2, I'm going to store at shellcode position 6. Jigsaw index 3, shellcode position 8, so on and so forth, right? So I'm just going to move through that, except we're in a 0 index world, so all those numbers are -1. But that's how that works. I now just read my positions, and I do a lookup, figuring out where is this byte and where does it need to go using this code, and I reconstruct the payload. And it worked relatively well. Only 4 engines detected that, so that is another pretty good option for obfuscating your payloads. So my coworker Corey was thinking about another way of obfuscating shellcode. He came up with this technique called it like offset. I can't remember what we called it originally, but it turns out like this is known as delta encoding. It's actually a known technique. The way it works, I take my shellcode and I store the first byte of the shellcode in a variable. And then in a new variable, I subtract my current byte from the previous byte. So I've stored the first byte of shellcode, so now I'm on the second byte of shellcode. The value that I store is the second byte of shellcode minus the previous byte of shellcode. And then I shift over and do the same thing. So now I'm storing the delta, the offsets between those bytes. And if you're using an unsigned array to store your shellcode, you don't even have to do any complicated math because the number wraps around. If you subtract one value from another value and the result is less than 0, the compiler or the computer will automatically rotate that around for you to the other side. Yeah, I know, Jeff. Like I was doing it with complicated math, adding the number. Is it negative? Add 256 or add 255. Turns out you don't have to do that. Using an unsigned variable, it just wraps around for you. It's magic. So if you had the bytes FC4883E4, you would have a variable that's called first byte or whatever that stores FC. Your obfuscated shellcode array stores 4C, 3B, and 61, which is the result of subtracting the second byte, or subtracting the first byte from the second byte from the third byte, so on and so forth, right? So all we're doing is storing the difference. And that was only detected by 2 engines. So that's another very viable option for obfuscating our payloads. I've mentioned a few times about signatures being detected. Many times the shellcode that's obfuscated isn't detected. What they detect is the pattern that we use. So just like that allocate memory, copy memory, execute shellcode pattern, there are recognizable patterns associated with different types of encryption or obfuscation methods. And vendors will write signatures for those. Unfortunately, signatures are very, very brittle and are very easy to break. All we need to do is make our program do something different in the process. Now, if you're familiar with compiling programs, you might have heard of compiler optimization. The compiler optimization looks at your code, says, you know what, you suck at programming, and I'm going to make your code more efficient for you. And you've got this whole branch of code over here that's never actually used, so I'm just going to optimize it out. It doesn't even need to be in your program. Oh, this thing you're doing here, you could actually do it much faster, so I'm going to make it faster for you. It makes those decisions. Unfortunately, if we're trying to insert like junk stuff to change our signature, compiler optimization might actually optimize those mistakes, as far as the compiler is concerned, out of our code. So you might need to compile with compiler optimization disabled. But by doing that, we can change the signature. Doing anything unexpected, like lots of times just inserting a printf. Like, so if you're in C, do a printf, and don't actually print anything out. Just call printf with an empty string in the middle of your code, in the middle of your deobfuscation routine, is enough to change the signature, because now we have multiple calls and we've inserted one of these in there. It's a different signature now. And they don't know all the different ways that you could insert junk code, so the signature is broken. You can try writing to the null device, and just writing to the null device, the bits go off into the ether, nothing changes, but it's a different signature. I've even seen simply opening the null device in the middle of the routine and closing it being enough to change the signature. So, as I mentioned, I wrote this 14-part blog series earlier this year where I analyzed these methods and other methods that I didn't talk about here. You can see the results. The 2 best performers were the Zor with multi-byte key and Corey's offset method. Then Jargon, tied with Jigsaw, was reverse byte order. And then, base 64 and no obfuscation at the bottom. So there's different options. And any of these in the middle might actually be a better choice for you, depending on what AV or EDR engine your target is using. If you can profile your target and find out that information, it should inform what you're going to use on your campaign. Because if you know that this technique doesn't work against CrowdStrike, but it works against Silence, and your target's running Silence, it doesn't matter if it scores higher, because that technique works against Silence to get around and not detected. So if you want to read the blog series, you can find it here. If you're a person who likes to hear things rather than read things, that is not me. Please give me the printed directions. I don't want a video on how to do it. But if you are not a ranty old man like me and you like to watch videos, there's also a corresponding video for every one of these blog articles. And if you want the code examples, there's a GitHub repo called Chromatophore that's at the Red Siege GitHub. And Chromatophore contains the code examples to generate obfuscated shellcode, and then that C or C# program that I talked about to just compile it and spit out the deobfuscated result to validate it works. You can find all the code examples here. Full disclosure, like I said earlier, this is just about hiding your shellcode, because that's only one part of the equation. I've got to hide my shellcode, but I also have to do things that are OPSEC safe down the rest of the line. I have to be able to get my shellcode into memory and execute it in a way without getting caught. And that is a lot harder to do. I come from the Defender world. I come from a system, our long history of system administration and being a Defender. So I feel bad sometimes releasing things like jargon and jigsaw that are hard to defend against, but it's only one piece of the chain. Like, I still have to do everything else after that correct. And if I screw up once and you guys are paying attention, it doesn't matter if my shellcode was obfuscated, you caught me. So I do want to say that I do feel a little bit bad, but I feel your pain. Other obfuscation ideas. So steganography, anyone heard of steganography? All right, and I'm way ahead of schedule, so I'm flying. Guys should have told me to slow down. So steganography. So steganography, for those of you that don't know, it is encoding data in an image. You do that by manipulating the least significant bit of one of the color channels, so RGB, and in things like PNGs that have an alpha channel that controls the brightness of that pixel. You can also encode in the alpha channel. And you can encode a lot of information into an image without significantly degrading the quality. And it's not something that we see a lot. I think it's probably something that Tammy's more familiar with. I'm sure you've seen some malware campaigns using Stego. That's like where we hear about Stego. And in C2 challenges, like those are the only two places you hear about people using Stego. But doing steganography could be a way of hiding shellcode. All you have to do is have your loader either be packaged with an image or make an innocuous call out to the internet to take a look at an image. And if you build in enough things that your loader is like grabbing different resources, it looks like something legitimate, it downloads this image and your shellcode is stored in that image. If you're familiar with Casey Smith, sometimes sub-T, although he seems to have left social media for good this time, sub-T Casey is the GOAT, and he has come up with so many techniques that us offensive engineers use. And he proposed this idea of a big integer. So a big integer in .NET languages is a really big integer. And it's stored as a large hex number. What else do we store as a large amount of hex? Shellcode, yeah. So you can actually store your shellcode as a big integer and then copy it into memory. And so there's another way of storing it, and it's not an array, it's a different data type, so that changes, the calculus a little bit for the EDR vendors. A big integer does actually work. You could store your shellcode in a resource file, like an icon file. So that is something that's been around a long time, actually like compiling a resource file that contains your shellcode, and it's separate from your source code. It's part of the final executable, but it shows up in a different section. So if you're familiar with analyzing executables, you've got different sections, like the resource section, the text section, different sections within those executables. And if you're putting your shellcode in a resource file, it goes into a different location of the executable. So if you have an engine that's analyzing entropy, some of the engines look at the entropy of the overall file. Some will look at entropy in specific sections. And normally, it's found in the text section, I believe, was where our payload's going to be. But if it's in the resource section, that might be a way of getting around a particular type of detection because they're only analyzing entropy and looking for badness in the text section. Store your shellcode in a separate file. I mentioned that earlier. So whether that's a file that you package with your loader or a file that your loader goes out and retrieves, that is something you could do. And as I said, pull shellcode from a remotely hosted location. So these are some of the ways that we can obfuscate shellcode and hide. It's a fun game. It's a fun challenge. So with that, this is me. If you have any questions, I'm Mike at redsiege.com. I'm Hardwater Hacker on a lot of the socials. If you like nature and wildlife and landscape photography, stuff like that, I'm Hardwater Hacker on Instagram and Threads. Follow Red Siege and you'll find out about new blogs that we've written, webcasts that we have coming up, things like that, places we're going to be talking. Feel free to send me a request on LinkedIn. We have a Discord. I'm biased, but I think it's a really good Discord. It's a really helpful community. We've had people that have gotten jobs come back and thanked us for the support and the things they learned in our Discord. It's all about helping people out because that's how I got here, is people helping me. So we'd love to have you. And we have this thing called the Wednesday Offensive every Wednesday, 12:30 to 1 Central Time. Hard stop at 1, no slides, no BS. We have interesting people doing interesting things in security, both offense and defense, coming on, talking to us about what they do, asking questions. People will type questions in chat. People will unmute their mics and ask questions. Scooby's been on there a bunch of times, you know, participating. It's a great time. We'd love to have you. And as I said, if you want the slides, you can get them at redsiege.com/hiding. This is us. My marketing guy makes me show this to you, and obligation fulfilled.
Questions? Oh, lots of them. Mike, that's hot.
Yeah.
It's
right over here.
Let's start down here.